Dear students, I am K.K.Thakur from Yogeshwari Mahavidyalaya, Ambadurga. Today we are going to study chapter Electrostatics. Before going to start actual part in Electrostatics from standard 12th, we will first of all revise the electrostatics chapter as you have already learned previously. In electrostatics, the meaning of electrostatics is the branch of physics which study the electric charges at rest, and in this electrostatics we again study the interaction between electric charges. So electrostatics is nothing but the branch of science which deals with the study of electric charges at rest and interaction between them. Regarding electrostatics, we have studied Coulombs Law. And the statement of this Coulombs Law is the force of attraction or repulsion between two-point electric charges at rest is directly proportional to the product of magnitude of the two charges and inversely proportional to the square of distance between them. And according to this Coulombs law, the mathematical form of Coulombs law is the force of attraction. The magnitude of force of attraction or repulsion between two-point electric charges at rest is equal to 1 upon 4 pi epsilon 0 Q1 into Q2 divided by R square, where Q1, Q2 are the two-point electric charges situated in a medium of permittivity epsilon, and this epsilon is equal to epsilon 0 k. Or these two particles are situated in a medium, vacuum or air, and distance of separation between these two charges is r. If these two charges are positive, then there is a force of repulsion between them. If one of the charge is positive and second charge is negative, then there is the force of attraction between the two charges. So Coulombs law gives the magnitude of force between two-point electric charges at rest and is given by formula 1 upon 4 pi epsilon 0 Q1 into Q2 divided by R square. And in this formula, epsilon 0 is called as permittivity of free space or vacuum, and the value of this permittivity of free space or vacuum is epsilon 0 is equal to 8.85 into 10 to the power minus 12 Coulomb square per Newton meter square. So this is all about Coulombs law, and this Coulombs law is useful in deriving the expression for electric field intensity, or simply it is called as electric intensity. So the strength of electric field, if a charge is situated in a medium, then it produces electric field surrounding it. and the strength of this electric field is determined by the vector quantity, and that vector quantity is called as electric intensity. And this electric intensity is defined as the force acting on unit positive charge. So electric intensity is nothing but force acting on unit positive charge placed at that point. Again, by using Coulombs law, if we derive the relation for electric intensity, then the magnitude of electric intensity at a point due to point charge is given by the formula E is equal to 1 upon 4 pi epsilon 0 Q divided by R square. And as the electric intensity is a vector quantity, if charge is positive, then electric intensity is directed away from the charge. If the charge situated in a medium is negative, then this electric intensity is directed towards the charge. So electric intensity is nothing but force acting on unit positive charge, and by using Coulombs law we derive the expression for electric intensity, and the magnitude of electric intensity is given by the formula 1 upon 4 pi epsilon 0 Q divided by R square. As the electric intensity is a vector quantity, if the charge situated in a medium is positive, then the electric intensity is directed away from the charge, and if the charge situated in a medium is negative, then this electric intensity is directed towards the charge. Again, from formula E is equal to F divided by Q0, the SI unit of electric intensity. So SI unit of electric intensity is Newton per Coulomb, or it is also called or written as Volt per meter. So these are the SI units of electric intensity. Again, we know that if a point electric charge is situated in a medium, then it produces an electric field in the surrounding region. Suppose that a charge plus Q is situated in a medium of permittivity epsilon is equal to epsilon 0k, then this charge will produce electric field in the surrounding region. So this is the electric field produced by the charge. And if we bring a charge plus Q0, which is a test charge or which is a free charge, then as electric field produced by the charge is positive, and we bring a charge which is also positive, but it is a test charge or free charge, then there is a repulsion between these two charges, and due to that this test charge will follow a path, and the path followed by the free positive charge is called as electric lines of force. So electric lines of force is nothing but the path along which free positive charge moves when placed in electric field. So this is the concept of electric lines of force. But these electric lines of force are imaginary lines, and these electric lines of force are used to express electric field pictorially or diagrammatically. So, the concept of this electric lines of force was introduced by the scientist Michael Faraday, and the concept of this electric lines of force is used to represent electric field pictorially or diagrammatically, and it has several properties. Again, by the use of electric lines of force, we are going to study another concept in electrostatics, which is called as electric flux, which is denoted by letter phi or suffix E, that means electric flux. So, electric flux is nothing but the total number of electric lines of force, or it is also called as tube of force, passing normally through given area in electric field. So, electric flux is nothing but total number of electric lines of force passing normally through given area in an electric field. And this electric flux is a scalar quantity. And this electric flux for small area ds, d phi for area ds is equal to vector E dot ds, vector ds. So electric flux is the dot product of electric intensity and surface area vector. Again, depending upon the surface area which is perpendicular to electric intensity, or surface area is parallel to electric intensity, or surface area is not perpendicular to direction of electric intensity, there are three cases regarding the electric flux. Suppose that, number one, if area ds, which is in the electric field produced by the charge, and if this area ds is perpendicular to electric intensity, then the electric flux through area ds is d phi passing through ds and is given by formula E into ds. And the value of this electric flux when area ds is perpendicular to electric intensity is maximum. So maximum electric flux is flowing through the area ds when area ds is perpendicular to electric intensity. Now second case, when this area ds is not perpendicular to the direction of electric intensity, or ds and E are not perpendicular, then we have to draw normal to this area ds. If we draw normal to area ds, then theta is the angle between electric field intensity and normal drawn to the area ds. And in this case, the electric flux d phi over again ds is given by formula the component of electric intensity, which is E cos theta multiplied by ds. So E ds cos theta is the value of electric flux through area ds when area ds is not perpendicular to the direction of electric field, in which theta is the angle between electric field intensity and normal drawn to the area ds. Again, third case regarding the electric flux is if the area ds is parallel to the electric field. So this is the area ds and this area ds is parallel to the electric field. Then in this case d phi over ds is equal to 0. So in case of electric flux, we have studied that the electric flux is equal to 0 only if theta is equal to 90 degree. So this condition is obtained from general formula when area ds is not perpendicular, d phi is equal to E ds cos of theta. If theta is equal to 90 degree, then the electric flux is equal to 0, and in that case surface area ds is parallel to the electric intensity. In second case, if theta is equal to 0 degree, then electric flux is equal to E into ds. That means maximum electric flux is passing through area ds. And finally, the last expression is d phi is positive. So d phi is positive when angle theta is less than 90 degree. If the angle theta between electric intensity and normal drawn to area ds is less than 90 degree, then electric flux becomes positive. And final case is the electric flux through area ds is negative if angle theta between electric field intensity and normal drawn to the area ds is greater than 90 degree. So this is an important concept in electrostatics which is very useful in studying the Coulombs law in electrostatics. So electric flux is nothing but the product of normal component of electricity and area ds, and there are four cases. Electric flux becomes 0 if theta is equal to 90 degree. Electric flux is maximum, which is equal to E into ds when theta is equal to 0 degree. Electric flux is positive when theta is less than 90 degree, and lastly the electric flux becomes negative if theta is greater than 90 degree. After this concept of electric flux, we will study new concept in electrostatics, and which is known as tube of force. So tube of force, as we have already studied, number of electric lines of forces can be drawn at every point on the electric field. If suppose this is the electric field formed by the point electric charge, then at every point on this electric field we can draw large number of electric lines of forces. And if these large number of electric lines of forces are drawn, then it is impossible to distinguish one electric lines of force from the another line. And hence again Michael Faraday introduced the concept of tube of force in order to study quantitatively electric field. So in order to study quantitatively electric field, that means electric field is studied in both magnitude and direction. Michael Faraday introduced the concept of tube of force, and the tube of force are nothing but a group of limited electric lines of force forming a tube-like structure passing through area in a permittivity of medium epsilon. So, group of limited electric lines of force forming a tube-like structure. That means large number of electric lines of forces. We cannot distinguish one line from each other. If these lines, which are limited in numbers, are enclosed in a tube, then this tube-like structure is called as tube of force. This is the imaginary tube. And according to the concept of tube of force, again Faraday explained that how many tubes of force can be originating from a given charge. Now, if the charge is unit positive charge, so from a unit positive charge, the number of tubes of force originating are one divided by epsilon. So from a unit positive charge, number of tubes of force originating are 1 divided by epsilon, or which is equal to 1 divided by epsilon 0 k. If a charge is positive q plus q charge, then from this plus q charge plus q, the number of tubes of force originating is equal to q divided by epsilon 0 k. So how many tubes are originating from unit positive charge, or how many tubes of force are originating from the charge plus q? In this expression, we notice that there is a term which is K, that is dielectric constant of the medium. If the charge situated in a medium, the medium is changed, then the number of tubes of force originating from charge also changes. And the SI unit of this number of tubes of force originating from charge is obtained from the equation q divided by epsilon 0 k. As we know that the SI unit of charge is coulomb, and the SI unit of epsilon 0 is coulomb square per Newton meter square, then this coulomb gets cancelled, and the SI unit is Newton meter square per coulomb. And we must notice that this is the SI unit of electric flux also. And we know that electric flux is given by the maximum electric flux d phi is equal to E into ds. And the value of electric intensity, or the SI unit of this electric intensity, is Newton per coulomb, and the SI unit of this area ds is meter square. So the SI unit of this electric flux is equal to Newton meter square per coulomb, and again the SI unit of number of tubes of force originating from the given charge is also equal to Newton meter square per coulomb. And as the number of tubes of force originating from the given charge changes if the medium in which charge is situated is changed, and therefore again Michael Faraday introduced another concept, and that concept is called as tube of induction. Then what do we mean by tube of induction? In case of tube of force, if the charge situated in a medium, if that medium is changed, the number of tubes of force also goes on changing. To avoid this, Faraday introduced the concept of tube of induction. And this tube of induction are nothing but the tube of force irrespective of dielectric medium. That means the value of number of tubes of induction originating from the charge does not depend on the medium in which charge is situated. And according to the concept of tube of induction, again, if a charge is unit positive charge, then the number of tubes of induction originating is equal to 1. That means one tube of induction is originating if the charge is unit positive charge, and if a charge is plus q, then the number of tubes of induction originating from the charge plus q is equal to q. That means q tubes of inductions are originating from charge plus q, and this concept or this tube of induction are independent on the dielectric medium. And by using the concept of tube of induction, again we define the term known as normal electric induction. In short, it is called as NEI, normal electric induction. And this normal electric induction is nothing but number of tubes of induction passing normally through unit area drawn around a point in electric field. So normal electric induction are nothing but how many tubes of induction are passing normally through unit area drawn around a point in an electric field. And to explain this normal electric induction, suppose that a charge plus q is situated at the center of a sphere having radius small r. And now consider a point P on the surface of the sphere and consider a small area ds, along the point P. Then, as surface is the sphere, the electric intensity at every point is directed radially outwards. So, a charge plus Q, when situated at the center of the sphere, the electric intensity on small area ds is directed radially outwards. Then by the definition of normal electric induction, the number of tubes of induction originating from charge plus Q divided by area of sphere, this gives normal electric induction. So normal electric induction is the number of tubes of induction originating from charge plus Q per unit area, that means divided by area of the sphere. And from this we obtain normal electric induction is equal to the number of tubes of induction originating from charge plus Q, which is equal to Q, and divided by the area of the sphere is 4 pi r square. And if we multiply and divide this equation by epsilon, that means permittivity of the medium, then this expression becomes Q divided by 4 pi epsilon r square multiplied by epsilon. As we know that the term 1 upon 4 pi epsilon into Q divided by r square is nothing but the electric field intensity, or simply electric intensity, and therefore normal electric induction is equal to epsilon into E. That means normal electric induction is nothing but the product of permittivity of the medium and electric field intensity. Again, we can obtain the SI unit of normal electric induction by substituting the SI unit of epsilon and SI unit of electric field intensity. And depending upon this normal electric induction, the final term we are going to study today is known as total normal electric induction. So total normal electric induction, in short, is called as TNEI, and this TNEI is defined as total number of tubes of induction passing normally through area ds, or total number of tubes of induction passing normally through given area is called as total normal electric induction. And this concept is very useful to study Gauss law in electrostatics. So total normal electric induction, by the definition, it is total number of tubes of induction passing normally through given area. We can write TNEI is equal to normal electric induction multiplied by area ds. Again, in this case, we study the two different cases. If area ds is perpendicular to electric intensity, then total normal electric induction is equal to epsilon E into ds. Second case, if the area ds is not perpendicular to the direction of electric intensity, then the total normal electric induction is given by the formula epsilon E cos theta into ds. So these are the formulas for total normal electric induction for small area ds. If area ds is perpendicular to electric intensity, if area ds is not perpendicular to electric intensity, then Tn Ei over ds is equal to epsilon E cos theta into ds. And if we consider the total surface area or whole surface, then the total normal electric induction for entire surface or whole surface is written as integration over closed surface epsilon E cos theta into ds. And from this formula we find the unit of total normal electric induction is Coulomb, and this total normal electric induction, again it is independent of dielectric constant of the medium, that is K. So today we have revised chapter electrostatics as we have already studied in standard 11, and few new concepts such as tube of force, tube of induction, normal electric induction and total normal electric induction, which will useful in studying Gauss law in electrostatics. Dear students, in my next lecture we will going to study the first article known as Gauss law or Gauss theorem and its